Introduction. Today we'll learn determinants. What are the determinants, teacher? First of all, tell me, can we represent matrix through single value? Yes, teacher. How? Okay, I will tell you. With the help of determinants, we can represent the matrix through single value. In this lesson, you will learn about determinants. Objectives. At the end of this lesson, you'll be able to find the determinant of a matrix, solve the determinants through the use of its properties, find the area of triangle by using determinants, find the inverse of a matrix, solve the system of equations using determinants and matrices. Determinant. If we associate a number of function with each square matrix, then that quantity is called the determinant of the matrix. A matrix which is not square does not possess determinant. Let A equals to Aij be a square matrix of order n. The determinant of A is denoted by, let A is equal to row-wise first row PQ, second row RS, then determinant of A can be written as determinant of a matrix of order 1. Let A equals A11 be a square matrix of order 1. The quantity A11 is defined as the value of the determinant of A. Determinant of A equals A11. For example, if A is equal to -5, then determinant of A equals -5. Determinant of a matrix of order 2. Let A equals row-wise first row AB, second row CD. The determinant is found as blue means positive plus AD, red means negative minus BC. So we have determinant of A as A times D minus B times C. Determinant of a matrix of order 3 cross 3. Let A equals row-wise first row A11, A12, A13, second row A21, A22, A23, third row A31, A32, A33. The determinant of order 3 can be expanded using first row as A11, A11 plus A12, A12 plus A13, A13, where A11 is equal to A12 is equal to, A13 is equal to. After solving, we have determinant of A equals A11 times of A22 into A33 minus A23 into A32 minus A12 times of A21 into A33 minus A23 into A31 plus A13 times of A21 into A32 minus A22 into A31. We also get same result through the expansion from second row and third row. Example. Find the determinant of the matrix A equals row-wise first row 2, 5, second row 1 minus 3. Solution. For the matrix A equals to row-wise first row AB, second row CD. The determinant of A equals AD minus BC. In the given question, matrix A equals row-wise first row 2, 5, second row 1 minus 3. So we get A equals 2, B equals 5, C equals 1, D equals -3. So determinant of A equals 2 into -3 minus 5 into 1 equals -6 minus 5 equals -11. Find the determinant of the matrix A equals row-wise first row 3, 0, -1, second row 2, -5, 4, third row -3, 1, 3. Solution. For the matrix A equals row-wise First row A11, A12, A13. Second row A21, A22, A23. Third row A31, A32, A33. The determinant of A equals A11 times of A22 into A33 minus A23 into A32 minus A12 times of A21 into A33 minus A23 into A31 plus A13 times of A21 into A32 minus A22 into A31. In the given question, matrix A equals row-wise first row 3, 0, minus 1. Second row 2, minus 5, 4. Third row minus 3, 1, 3. So determinant of A equals 3 times of minus 5 into 3 minus 4 into 1 minus 0 times of 2 into 3 minus 4 into minus 3 plus minus 1 times of 2 into 1 minus of minus 5 into minus 3. By solving it, we get minus 44. Properties of determinants. Property 1. The value of the determinant remains unchanged if its rows and columns are interchanged. Property 2. If two rows or columns of a determinant are interchanged, the sign of the determinant is changed. Property 3. If two rows or columns of a determinant are identical, then its value is 0. Property 4. If all the elements of a row or column of a determinant are multiplied by a constant k, then the determinant is multiplied by k. Property 5. If some or all elements of a row or column of a determinant are expressed as sum of two or more terms, then the determinant can be expressed as sum of two or more determinants. Property 6. If any row or column of a determinant, a multiple of another row or column, is added or subtracted, the value of the determinant remains the same. Example. Using properties of determinants, evaluate. Solution. We have, by taking 7 common from the first column 1 and 2 are identical, so the value of the determinant is 0, equals 7 into 0 equals 0. Example. Evaluate the determinant. Solution. Let delta equals to. Apply operation R1 approaches R1 plus R2 plus R3. We get all the elements of one row becomes 0, so the value of the determinant is equal to 0. Area of triangle. The area of triangle ABC, whose vertices are A x1 y1, B x2 y2, C x3 y3, is 1 by 2 x1 into y2 minus y3 plus x2 into y3 minus y1 plus x3 into y1 minus y2. It can be written in the form of determinant as follows. Points to remember. The area is always a positive quantity, so we always take the absolute value of the determinant for the area. The points A, B, and C are collinear if the area of triangle ABC is equal to 0. Example. Using determinants, find the area of the triangle whose vertices are minus 3, 5, 3, minus 6, and 7, 2. Solution. The area of the triangle with vertices minus 3, 5, 3, minus 6, and 7, 2 is given by the following determinant. Equals 1 by 2, minus 3 into, minus 6, minus 2, minus 5 into 3, minus 7, plus 1 into 6 plus 42, equals 1 by 2, 24, plus 20, plus 48, equals 46. The area of the required triangle is 46 square units. Minors and cofactors. This minor is the minor determinant that is left after removing all the elements in the same row and same column. For example, in the determinant, the minor of A1 is this. Cofactor. The cofactor of an element is the corresponding minor multiplied by -1 raised to the power m plus n, where m and n stand for the number of row and column in which the element lies. In the determinant above, the cofactors of the elements A1, A2, A3, B1, B2, B3, and so on, which are represented by A1, A2, A3, B1, B2, B3, and so on, are the corresponding minors multiplied by +1 and -1 alternately. Example. Find all the minors and cofactors of the elements. Solution. Let A11 equals 4, A12 equals 3, A13 equals 1, A21 equals 1, A22 equals 3, A23 equals 2, A31 equals 2, A32 equals 1, A33 equals 5. M11 equals minor of A11 equals this, which is equal to 15 minus 2 equals 13. M12 equals minor of A12 equals this, which is equal to 5 minus 4 equals 1. M13 equals minor of A13 equals this, which is equal to 1 minus 6 equals minus 5. M21 equals minor of A21 equals this, which is equal to 15 minus 1 equals 14. M22 equals minor of A22 equals this, which is equal to 20 minus 2 equals 18. M23 equals minor of A23 equals this, which is equal to 4 minus 6 equals minus 2. M31 equals minor of A31 equals this, which is equal to 6 minus 3 equals 3. M32 equals minor of A32 equals this, which is equal to 8 minus 1 equals 7. M33 equals minor of A33 equals this, which is equal to 12 minus 3 equals 9. Below are the cofactors. Adjoint and inverse of a matrix. Let A equals Aij be a square matrix. The adjoint of A is defined as the transpose of the matrix Aij, where Aij is the cofactor of the elements Aij in the determinant of A. It is denoted by adjoint A. Thus, adjoint of A is equal to transpose of the matrix of cofactors of Aij. Singular matrix. Let A be a square matrix. Matrix A is said to be singular if determinant of A is equal to 0. If determinant of A not equal to 0, then the matrix is said to be non-singular. Example. Find the adjoint A, where A is equal to row-wise. First row, 1, 2, second row, 3, 4. Solution. Given A equals row-wise, first row, 1, 2, second row, 3, 4. The cofactors of the matrix A are A11 equals 4, A12 equals minus 3, A21 equals minus 2, A22 equals 1. Therefore, adjoint of A equals row-wise. First row, 4, minus 2. Second row, minus 3, 1. Adjoint and inverse of a matrix. Theorem 1. If A be any square matrix, then A into adjoint A equals adjoint A into A equals determinant of A into I, where I is the identity matrix. Theorem 2. If A and B are non-singular matrices of the same order, then AB and BA are also non-singular matrices of the same order. Theorem 3. The determinant of the product of matrices is equal to the product of their respective determinants, that is, determinant of AB equals determinant of A into determinant of B, where A and B are square matrices of the same order. Theorem 4. A square matrix A is invertible if and only if A is a non-singular matrix. Inverse of A is equal to 1 by determinant of A into adjoint A. Example. Find the inverse of A equals row-wise. First row 2, 5. Second row -3, 1. Solution. Given A is equal to row-wise. First row 2, 5. Second row -3, 1. Determinant of A is equal to 2 minus 5 into -3, which equals 17, which is not equal to 0, hence inverse of A exists. The cofactors of the matrix are A11 equals 1, A12 equals -3, A21 equals -5, A22 equals 2. Therefore, adjoint of A is equal to row-wise. First row 1, -5, second row 3, 2, and inverse of A is equal to 1 by 17 into matrix row-wise. First row 1, -5, second row 3, 2. Applications of determinants and matrices. Consistent system. A system of equations is said to be consistent if its solution exists. Inconsistent system. A system of equations is said to be inconsistent if its solution does not exist. Criterion of consistency. For a given system, AX is equal to B, X equals inverse of A into B of linear equations, where A is a square matrix, we have the following criterion for the consistency or inconsistency. If determinant of A is not equal to 0, the system is consistent and has a unique solution. If determinant of A is equal to 0 and adjoint of A into B is 0, the system is consistent and has infinitely many solutions. If determinant of A is equal to 0 and adjoint of A into B not equal to 0, the system is inconsistent and has no solution. Example. Use matrix method to solve the system of equation. X plus 2y equals 4. 2x plus 5y equals 9. Solution. Given x plus 2y equals 4. 2x plus 5y equals 9. The system of equations can be written in the form Ax equals B, where A equals row-wise first row 1, 2, second row 2, 5. X equals row-wise first row X, second row Y. B equals row-wise first row 4, second row 9. Determinant of A equals 5 minus 4 equals 1, which is not equal to 0. Hence, A is non-singular matrix and therefore its inverse exists. The adjoint of matrix A is row-wise first row 5 minus 2, second row minus 2, 1. Inverse of A equals 1 into matrix A row-wise first row 5 minus 2, second row minus 2, 1. We know that Ax is equal to B. X equals inverse of A into B. Put the value X inverse of A and B. Matrix X row-wise first row X, second row Y equals matrix A row-wise first row 5 minus 2, second row minus 2, 1 into matrix B row-wise first row 4, second row 9 equals matrix row-wise first row 2, second row 1. Hence, X equals 2, Y equals 1. Did you know? Takakazu Sekikawa, the Japanese mathematician, developed the idea determinants and their expansion. Laplace gave the idea of determinants cofactor expansion. Summary. Let us summarize what we have learned. If we associate a number of function with each square matrix, then that quantity is called the determinant of the matrix. Following are the properties of determinants. The value of the determinant remains unchanged if its rows and columns are interchanged. If two rows or columns of a determinant are interchanged, the sign of the determinant is changed. If two rows or columns of a determinant are identical, then its value is 0. If all the elements of a row or column of a determinant are multiplied by a constant k, then the determinant is multiplied by k. If some or all elements of a row or column of a determinant are expressed as sum of two or more terms, then the determinant can be expressed as sum of two or more determinants. If to any row or column of a determinant, a multiple of another row or column is added or subtracted, the value of the determinant remains the same. The area of triangle in the form of determinant is as follows. This minor in the minor determinant that is left after removing all the elements in the same row and same column. The cofactor of an element is the corresponding minor multiplied by -1 raised to the power m plus n, where m and n stand for the number of row and column in which the element lies. The adjoint of A is defined as the transpose of the matrix Aij, where Aij is the cofactor of the elements Aij in the determinant of A. A square matrix A is invertible if and only if A is a non-singular matrix. Inverse of A equals 1 by determinant of A into adjoint A. If determinant of A is not equal to 0, the system is consistent and has a unique solution. If determinant of A is equal to 0 and adjoint of A and B is equal to 0, the system is consistent and has infinitely many solutions. If determinant of A is equal to 0 and adjoint of A into B not equal to 0, the system is inconsistent and has no solution.